All right, this is a little bit about how to do the beam and girder calculations for civil engineering. Today is a day where we are going to review the interior beam and the exterior beam problem. That video is something that you do need to watch in its entirety in order to receive credit for watching the video. When you're done, you should be able to show that you know how to do the interior beam, which is a review because we did that in the last class. And also, you should be able to show that you know how to do the exterior beam problem. In theory, that is due today, and you should have something that you can turn in to me. So here we go. If we are trying to do that interior beam calculation, what I did off of the website, and I'm going on today's folder, is I'm going to open some of the documents that I need to do that. One of them is this Z modulus chart. So let me just flip that and rotate it so it's facing the right way so we can read all the wonderful numbers that are in there and see what's on that. Another item that I need from Schoology is this spreadsheet. I believe you can open that in Schoology. So if you don't have a computer that can open it, you should be able to. I'm also pretty sure you can open that on your phone if you really need to. But there's that second spreadsheet. And then I do have the overall shortcut cheat sheet on how to do all the calculations. So I'm not going to keep flipping back and forth between this one and my PowerPoint presentation though, because I took all of these directions and I put them into the PowerPoint presentation. So I'm going to do calculation 1, 2, 3, 4, 5, 6, and 7, showing you how I did all those. So first off, I'm going to close that and get the PowerPoint presentation back up. So here is calculation number 1. This is the review of what we did in the last class. The first thing I did was I determined the beam load in pounds per linear foot. So to do that, I took the total load of 150 pounds and multiplied that by the tributary width. Now just so you know, the tributary width I got from the beam diagram that was on the homework assignment. I looked at the overall thing and I realized the beams are 18 feet in length. The girders are 20 feet in length. And the tributary width is 6 foot 8 inches. 6 foot 8 inches. But that's not really how you show a tributary width, because the tributary width means it's the area around the beam. So half of this side of the beam transfers to it and half of this side carries to it, which is basically the same size as the opening in between beams. So 6 foot 8 inches translates to 6.67 feet. When I calculated that, I got 1,000 pounds per linear foot. Moving on to problem number 2. You can use the beam shortcut formulas or MD solids to find the reactions in the max moment. This is what we spent the last few days of class working on overall. Just doing this calculation does take you 3 calculations, a graph, and another calculation. Or you can use the shortcut formulas. I demonstrated the shortcut formulas right here. In order to find the reaction force for a consistent load across the beam, you take whatever the pounds per linear foot is, that's what W is, times 18, that's the length of the beam, and divide by 2. And you get 9,000. And as you can see, that is the exact same number that I got from using MD solids. To find the max moment using the shortcut formula, I would take the total load times the length of the beam squared divided by 8. So here is my load times 18 foot squared. I got 40,500, which is the same that I got from MD solids. So if you're doing this at home, you don't have access to MD solids today because that is at school on the computer. So your only choice would be to use these reaction formulas. They're not that hard. I'm sure you'll figure it out. Give it a shot. Step 3, determine the nominal moment, which means we're taking the max moment of 40,500 pounds and increasing it by 67%. When I did that, I got this number right here. I then converted that number to inches by taking 67,635 times 12 divided by 1. And now my max moment, which is my nominal moment, is in pounds per inch. Nope, pound inches, not pounds per inch, pound inches. Using that number, I determined Z. And to determine Zx, I did that by taking the nominal moment divided by Fy. Now Fy has to do with how steel is manufactured in the United States of America. It's one of the grades of steel. It's steel grade 529. And when you use that steel, the yield or stress modulus is 50,000 pounds per inch squared. So if you take your number from the nominal moment and divide it by 50,000, you get 16.2 inches cubed. The pounds cancel out, the inches combine, which is where that comes from. Step 5 would be to take that 16.2 and look it up on one of the charts that we opened up just a few minutes ago that I seem to have closed by accident. So I will open it up again. There it is, and I'm going to rotate it so that it's facing the right way and zoom in. So on this chart I need to find 16.2, and I'm just going to go up, and once I find a number that's bigger than 16.2, and remember you should always be looking at the bold numbers, I'm always going to go one bigger. So I'm going to choose this one, 20.1. It's a beam W 12 by 16, and I need this number 20.1 and 103. Now the 103 number I actually don't really need today, because this is if we're going to do one of the last calculations by hand, which you could always do by using the beam shortcut formulas, or you can use MD solids. So since you are at home, you might want to take a look at that number and write it down. That's why we write it down all the time anyhow. So I wrote down the 20.1 and the 103 right there. I need a different chart to get these two numbers. And that other chart is the other spreadsheet that we opened. So on that spreadsheet, if I go up and select 12 by 16, I can get the TW, which is right there, of 0.22, and the depth of the beam right there, which is 12 inches. And I wrote all of those numbers right down here, and actually this is the first test we do, because the first test we do is that ZX that you choose for your beam has to be bigger than the ZX that you calculate. And the ZX I got for my beam when I looked it up is 20.1. The ZX I calculated is 16.2. So this is officially a pass for test number 1. Test number 2 is to check the shear strength. That means that when the beam would break, does this beam hold up? So in order to do that, you're going to find your reaction force. The reaction force is what we calculated back here in step number 2. Right here, 9,000 pounds. So you're going to take your reaction force and increase it by 50%. So 9,000 increased by 50% is 13,500 pounds. That is a real number. That is assuming some magical load of 50% greater than what I thought it would be is going to stand on top of my beam. What you compare that to is what the beam can actually hold. So this 50,000, as I said before, comes from how we manufacture steel in the United States. 12 inches is an actual number that represents how tall the beam is. And the 0.22 is the thickness of the beam. It's how thick it is. So it's roughly 1/4 of an inch thick, which doesn't seem like that much, but it's very strong. So if, this is how the beam is designed. So this beam, that's 1/4 of an inch, let's just call it 1/4 of an inch, times 12 inches, times 50,000, and this number over here is a correction factor that we just take that total limit, and we're going to say there was some manufacturing process that's only going to allow it to hold 60% of what it's designed to. And even with that taken into account, this beam will easily hold the biggest number that I think is going to be on it. Easily hold. Just for the record, I've never seen this test fail on any beam that we've selected ever for the course. So that brings me down to calculation number 7, which is the last one that we do, which is to calculate the deflection limit. And then compare it to what the real limit is, which apparently I cannot spell, so I will fix that right now. There we go. The real limit is. And apparently I couldn't spell it twice. All right. So to calculate the deflection limit, I took 18 feet times 12 to get how big my beam is in inches. And then you take that beam length in inches and divide it by 240. So this beam at most can deflect 0.9 inches. Once I ran it through the MD Solids calculation, which I did not do by hand, I did it on MD Solids, and I will show you that when I do the next one, I got 0.79. Since 0.79 is less than 0.9, because 0.9 is how much it can deflect, 0.79 is less, it passes the total load deflection test. The last thing we need to test is the live load only test. And to do that, you take your beam length in inches divided by 360. So the beam length in inches has not changed from up here, still the same. And if I take that number divided by 360, I get 0.6 inches is the most the beam can deflect. I ran this through MD Solids and got 0.52. And since 0.52 is less than 0.6, this is a pass. So to summarize the entire calculation that I took the whole hour to do the other day, it took me 11 minutes. So it's probably going to take me a little longer than that to show you the exterior beam, because I'm going to do some other things in MD Solids. Okay, so here we go. Here is the exterior beam. This was your homework that is due today. Since I'm reviewing this problem with you live right now, if you made any mistakes, feel free to correct those mistakes. I will collect this assignment from you and make sure that it was done properly. Obviously, since I'm going through it right now and providing all of the answers to you, I'm going to be fairly critical of your work, making sure that you do have all the right numbers and all the things written in the proper places. So the first thing that's different is this is going to be an exterior beam. And the main difference between an interior beam and an exterior beam is when I line this, this thing up on the outside of the building, only half of the load goes to the beam. So how is that represented in our calculations? Well, when I did all of my loads, I still have the same load, but it's only half of the width. So instead of being 1,000 pounds, this is only 500. So you can guess that when I do with the beam shortcut formulas, this number is going to be half of what it should be, and this number is going to be half of what it was before. So you could literally take the first set of problems and just whack it in half and whack it in half. And when you do that, that's what you get for your shortcuts. Now I am going to build this one in MD Solids and take a moment to do that because we haven't used it that many times. It's not that hard of a program to use. So to do that, I'm going to bring up MD Solids. And I'm going to build my beam by selecting the beam. It is an 18-foot beam, so make sure you put feet in right there. And it goes from 0 to 18 feet. The overall load on my beam is a consistent load of from 0 to 18, and it is half of what it was before, so it's 500 pound-feet. And when I hit enter, there you go, there's my max moment, there's my reaction force. This is exactly what I copied into the PowerPoint presentation. I'm going to leave that MD Solids program open because I'll need it at the end of this presentation when I do the deflection. Okay, moving on then. I am going to take my max moment and find the nominal moment by increasing it by 67%, and I get this number here. Just like I did before, I'm going to convert that number to inches, and I get this number right here. This is pound inches. Then I can find ZX. To find ZX, I take my pound inches number divided by 50,000, which comes from the steel, and I got 18.1. This is another moment where I'd like to take and do a little bit of a reality check, because when I did this test back here, this was 16.2. So when I'm doing it down here, and it's 18.1, that should make sense. It's half of what it was before. Now that's not true for all the numbers, so you can't just simply whack everything in half and be done. Because for example, when I did look on my ZX plastic modulus chart, which is here, when I'm trying to find an 8.1, this one looks like it would be big enough, but I'm going to go one past that. So I'm going to try to use this 10 by 12. The Z, I'll scroll up a little bit, ZX on the 10 by 12 is 12.6. IX on the 10 by 12 is 53.8. So I put those numbers into my presentation here. I looked up TW and D from the other spreadsheet that I opened. So this is a 10 by 12 beam, 10 by 12. I'm going to have to scroll way down. There it is. And TW is 0.19. D is 9.9. So I threw those in there. There we go. Next I checked, by the way, this is a pass because the ZX I chose is bigger than the ZX that I calculated. When I move forward, I'm going to take the reaction force of 4,500 pounds. That's what I calculated in number 2 of this problem. I'm going to increase it by 50%. So when I do that, I get 6,750 pounds. That is what I think the maximum I would ever have to put on this beam is. Using numbers about the design of the beam, I'm calculating the maximum this beam can hold. So this is the steel it's made from. This is the height of the beam. This is the thickness of the beam. And I'm going to decrease all that by 60%, and I get this. This is easily a pass because this beam is designed to hold 10 times more than what I'm ever going to put on it. The last thing that I need to look at is how I am calculating my deflection limit, followed by how I'm getting that number out of MD solids. So to calculate the deflection limit, I'm going to take the length of my beam in inches divided by 240. So the beam is still 216 inches, which is 0.9, same thing it was in the first problem. But then how did I get this out of MD solids? So to find that number from MD solids, once I have this, I'm going to go up here to the top and I'm going to click on Options. Go down to Design because I'm going to design a beam and click. Over here I'm going to build my beam by doing a cross section, which I think is the easiest way to do it. So I click on cross section and I'm going to call it a standard beam. Click. Use the US American steel, and our beam is a flange beam. It's a W beam. That's the beam we're doing. So it's the W 12 by 16 or whichever one I'm building. I forgot which one it was. And I'm going to click on it. The steel I need is the second one down. It's 529 grade 50. Click. This was the 10 by 12 beam, so I have to scroll all the way down to 10 by 12. Try to go a little faster here. There we go. 10 by 12 beam. 10. No, I went past it. 10 by 12. And hit compute. Now this information right here also has some of the same numbers that I had to write down before, like the TW and the IX and those things. I already wrote those down though, so I don't need to look them up again. But what I do now is go up here to Options, and instead of the shear moment diagram, I want to see the deflection diagram. And on that deflection diagram, right here, is where I get the deflection for the beam. And it says 0.75. So if I go back to my PowerPoint presentation, 0.75 is less than 0.9. That's a pass. One more time. Down here I'm going to calculate the deflection limit. This time I'm dividing by 360. So when I calculate the deflection limit and divide by 360, I got 0.6. I do need to build this beam in MD solids. Now the big difference when we're doing this is the live load, not the total load. So the live load was 66% of the total load, and 66% of 500 is 344. So where did I get that 66% from? Back up here. The live load is 100 out of 150. So that's 66% of the total load. So I could just take that number 550 times 66%, and then I would know what my live load is going to be. So I got to build that in MD Solids, and to do that I got to X out all of these windows. All of those windows. There we go. And start MD Solids from scratch. And when I do it, I'm going to select beam, select the two-ended beam. This is an 18-foot beam, and it is in feet. It starts at 0 and goes all the way to 18 feet. Now, I have a consistent load that goes all the way across the beam, and it is 334 pounds per foot. So there you go. All those numbers are going to be 66% of what they were before. So once again, I'm going to go up to Options, Slope and, Design, because I'm designing my beam, Cross Section, Standard, Steel, W-beam, click, select my grade as 529.50, go down and select the beam that I need, which is the 10 by 12, 10 by 12, 10 by 12, 10 by 12. Hit Compute, Options, Deflection. And this time it says that it's going to deflect by 0.50, 0.50. So if I go back to my presentation, there that number is right there. That's how I found that picture. And this should say, since 0.50 is less than 0.6 inches, which is what I got right here, this is a pass. So for the exterior beam, the 10 by 12 is the right beam to choose. At this point, my review of your homework and what we did in the previous class is done. So you should be done with this video. Be prepared to turn that homework assignment in the next time that I see you. And this video should have been watched in its entirety. The next part of class, you're going to watch a video on me showing you how to do the girder, which is different from a beam, just slightly, because it's a different type of beam. So once you see me do the internal girder, your homework will be to do the external girder.